All right. So I've got our three favorite devices here. So our three passive devices that we use all the time, right? So resistors, capacitors, inductors. All right. Now, you guys have you took circuits too. A lot of the elements of circuits too probably went into your brain and then out of your brain as you went through electronics. We do have to remember we're talking about power, we got to remember some of the things that you did see in circuits too. So we're going to be reviewing some of that. Okay, so I've got a capacitor, inductor, and a resistor, and I followed the passive sign convention with what I did here, which means I did what? If I followed the passive sign convention. Current's going into the positive, yeah. And so if I have a resistor here, what's our relationship? It's V, you guys know this for sure, but it's what? V equals IR, right? And if the current had been going the other direction, what would I have said? Negative IR, right? All right, so now what about for my capacitor? CD VDT, all right, so I of T equals CD VDT. Now we're not going to be doing much in the way of differential equations. All right. We will review that real quick because again, I just want to make sure we're on the same page with AC circuits. All right. What about for the inductor over here? V of T is what? LDI dt. Okay. LDI dt. Now, for the most part, we deal with steady state operation. All right. What does that mean if I say steady state operation? Well, let's say I've got this circuit here, and I got a voltage source and an R and an L. All right, most of the circuits that we're going to deal with in this class are R and L. All right, if I look at the grid, most of our loads that are in the grid are R and L type of loads. All right, and so I think motors and things like that, I've got L in a motor. I don't have a lot of capacitive devices. Okay? So I've got this example circuit here. What's the frequency in hertz of that voltage source that I hooked up to that thing? 100 hertz, right? 2 pi omega, right? So the frequency of that thing in hertz is that. All right. Now we're going to talk about how we would analyze this thing. But if I just was, I don't remember anything except what I wrote right here. Right? The God's honest truth of the world, those three things, right? How would I write out a circuit relationship that would solve for the current in this thing? KVL. To a KVL, right? And what would I do? If it were me, I would say 0 equals, and I go around in a circle like that. Right? And I would say 0 equals, I always label everything like this. So I would say 0 equals negative V of T plus VR of T plus VL of T. All right? That should make sense to you. All right. By the time I'm done, I would end up saying V of T is equal to I times R plus L di by dt. All right. And then, oftentimes we kind of rewrite this guy as V of T over R equals I plus L over R di by dt. We give that L over R thing a name, a time constant, right? I'm not going to focus too much on that because, again, I don't want to talk about differential equations. But this guy, what does the solution to this thing look like? I said, what is I of T? What's the general gist of what I of T is going to look like? There's two components to it, right? What are the two components to I of T? You guys weren't expecting me to get right into differential equations on the first couple minutes. Homogeneous in a particular, homogeneous in a particular, right? So, which I think of as a steady state, right, solution and a transient solution, right? That's a math way of saying it. It's a true statement, but it's a more mathy way to say it. A steady state and a transient. What's the transient look like? Is what? Well, so I see what you're saying. Yeah, so the steady state looks kind of like the input in the sense that if my input in this case was a voltage source that's sinusoidal, my steady state is also going to be a voltage source that is sinusoidal, right? So if I have V of T equals that that thing right there, I know that my steady state solution is going to be some value, I'll say I peak times cosine what? Same frequency. What do I always know about the steady state solution? Has the same frequency. It looks like the input has the same frequency. What can change between the input? So the input in this case, it's a Yahoo way of talking, outputs and inputs, right? So if I have an input here, my input's my voltage source, my output is my current, right? My output could be anything. It could be the voltage across the resistor, voltage across the inductor. I want it to be the current. All right. What's true about all the currents and all the voltages in that circuit in steady state? They all have the same frequency. How do they relate to each other? They have the same frequency. They're all sinusoidal. What can be different about them? The phase and the amplitudes, right there. They got different amplitudes and different phases. So here, what I end up saying is that current looks something like this. It's got some amplitude, it's got some phase shift. And our goal usually when you don't talk about the transients when you're working in electronics, right? You don't worry about that stuff. In fact, you don't even really worry about the phase typically in those cases. But what you're solving for in any of your transient analysis, you're solving for your phase and you're solving for your magnitude. Okay. All right. So we're going to talk about that. This is the steady state here. It's also on steady state SS. What's the transient look like? Well, yeah, sometimes we do call it DC, although it's not really DC. It's exponential, right? We say it's AE to the negative T over tau. All right, where tau is defined by the L and the R. It's been a while since you thought about this. I don't expect everybody to fully remember it. At a minimum, most likely, look, you're not going to go get a job at Duke and they're not going to say, here's a differential equation and solve it, right? You guys all know that by now, probably, right? But it's useful to remember that there is some sort of transient that comes out of these things. The transient is this decaying thing. All right, sometimes this is called a DC term. We worry about this, for instance, from talking about circuit breakers, right? I might worry about what this guy is because he impacts the way a circuit breaker might behave. All right, so there's reasons why we need to understand that stuff at least. All right, but looking at this, right, what I would have to do is I'd have to solve for these different things here. So tau is something I know. What's true about AE to the negative T over tau? We call it transient. What's that mean about it? Something that's transient does what? Changes and hopefully goes away. Hopefully it's gone after a while. It's transient. It's there for a little while and then it's gone. And in this case, how does this guy go away? Well, if I wait longer, E to the negative T over tau, the longer I wait, what happens to E to the negative T over tau? Approaches zero. Approaches zero, right? That guy should become zero. So this is my transient. Now, without getting into this, what is that going to make the current look like? If I wanted to look at this thing over time, if I went to an oscilloscope and I said, all right, oscilloscope, show me what the current looks like. What would that current look like? After a while, it would look like the steady state. Now, the transient would basically give me this guy over here, right? And the total solution is the sum of those two things, but the transient I only see for a little while, right? Why is this guy all the way up here? What made him be up there? What made the transient bit? First of all, why is there a transient response? You know how to solve for it. You probably don't know why it is. You may not even remember how to solve for it, but at one time you did, right? You probably never knew, what is the transient? Why is it there?
When you start it off essentially.
Yeah, when you start it up, what's the problem with this inductor?
Zero negative is 0.2.
Okay, zero negative is 0.2. Yeah, so what's the problem with that? That's right. The inductor, so inductors and capacitors, the thing about them is they don't like change, right? An inductor, if it's got a current through it, it wants to keep that current going through it, right? So if I suddenly changed at time t equal to 0, I applied that voltage source. If that guy had a current going through it, if the current at 0 minus was 0.2 amps, 0 minus means like a nanosecond before 0. What's it have to be like a nanosecond after 0? Same thing, all right? So basically, what this is saying is the voltage source is trying to push everything down here. But the initial condition said, you can't do that. I got to stay continuous in my current at T equals 0. Right? So eventually that thing kind of works itself out of the system. That is basically ultimately a statement of thermodynamics, basically that I have to keep energy constant. So what happens if I take a hair dryer? All right, what's a hair dryer? What kind of circuit is a hair dryer? Basically a resistor. Yes, there's motors in it because there's air moving. But the big thing inside of a hair dryer is the giant resistor that's heating up. Right? And it's probably drawing 10 amps. When I pull that thing out of the wall, what happens? You get an arc. You see a flash of light. Why do you see a flash of light? Because there's an inductor in that circuit, and you're forcing the current to become discontinuous. And current doesn't like to be discontinuous in an inductor because it represents energy storage. That energy that was electrical became light all of a sudden. All right. Same thing happens with the capacitor. If I put a screwdriver across the capacitor, you'll get a similar flash. Right? Energy likes to be stored. Right? And energy that's stored can't just go away. Right? It has to go from one form to another. Right? Now, I don't expect you guys to remember all of this stuff. The one thing I do think you probably should remember would be, okay, well, what if I just wanted to get the steady state piece? How would I get just the steady state piece of that? Do what?
Frequency domain.
Frequency domain, phasor domain. Yeah, frequency domain, phasor domain, you can call them different things. Really a Fourier transform if we want to get fancy. But basically we do phasor analysis. Okay. So how does that work? How's the whole phasor analysis work? If I want to do the steady state stuff, I got to go back to this idea of phasors. All right. Now I'm going to do something you probably didn't think about too much in electronics, but it's something that we're always going to do here. So let's say I've got this character right here. I wrote x of t is this. All right. Yes, sir.
Why in this class now does the phase matter, but before it didn't as much?
So in electronics, you didn't think, they don't talk about phase a whole lot. In fact, usually when you talked about, let's say, a capacitor, you would have said the impedance of the capacitor is probably 1 over SC or 1 over J. You used S a lot probably, and you made transfer functions and stuff, right? Usually in electronics, you're worried about amplifier design. So you're worried about what the amplitudes are going to do. And they're thinking about audio type of applications where phase doesn't matter. But when I'm in a power application, phase is going to matter because phase relates to the power conversion, the energy conversion that's happening in the system. In electronics, they're not worried about that stuff.
Does this mean combine the sources, they all have to be in the same phase, right?
Well, it's not so much that, it's really that the power, the rate of energy conversion, which is power, is related to the phase shift between the current and the voltage. And we're going to review all that stuff. We're going to talk about single phase power. You guys should have seen single phase power in electronics too. Sometimes you do, sometimes you don't. All right, we're going to review it. All right. And then we're going to talk about three-phase stuff. But I want to go into just the notion of the phasor because I want to get into an important point, which I know they don't really talk about much in electronics too, for one. Right? If I have that waveform right there, 10 cosine 2 pi 10t plus 45 degrees, what is the phasor for this guy? I would write it as, first of all, capital X, and you're going to see me write all my phasors like that. So I have a lowercase for my time domain waveform and an uppercase like that. What would the phasor be for that? 10 angle 45 is exactly what I was expecting you guys to say. I'm going to do everything like this, 10 over square root of 2 angle 45 degrees. Why did I divide by the square root of 2? RMS. All right, I did root mean squared. All right, if you get a voltmeter, if you get a voltmeter, you go to an electrician sticks a voltmeter into an electrical panel, it measures RMS. We don't ever measure the peak value. All right, what's the voltage coming out of that wall socket right there? 120. What is that? RMS or peak? It's RMS. All right, we talk of everything in terms of RMS. All right, root mean squared. The peak value of that voltage should be about 169 volts, right? Or really it's 120 RMS. So my phasors are all going to be written this way. And when I teach electronics two, or sorry, circuits two, right? What I typically do in the beginning of the semester when I introduce phasors, I leave them this peak. And then when I get the power, I convert them over to RMS. All right. I'm going to do everything in this class, assuming that those values are RMS, those magnitudes, because that's the standard way of doing AC circuit analysis. If you get a multimeter, that's what you measure with a multimeter. Okay. All right. So, I talk about making phasor diagrams. That's something we deal with quite a bit when we talk about power. What would the phasor diagram look like for this guy here?
That where the magnitude is the radius and like the angle is
The
far
magnitude.
along the circle it is.
Yeah, so we draw a vector here. So in this case, I'll say the magnitude is 10 divided by square root of 2. And then the angle, where do I measure angle from? Where's 0 degrees?
On the x-axis.
From the x-axis. And which way is positive angles? Yeah, counterclockwise, right? So this would be 45 degrees here. Okay. So I would draw it like that. Now, important thing is for my phasors, I reference everything to cosine, right? So I reference everything to cosine. So 10 cosine that, 45 degrees. So what happens if I give you these guys here? 10 cosine 2 pi 60t minus 90 degrees. What would the phasor be for this character? 10 over root 2 with what angle? Negative 90. Okay, that was easy. What about this guy? Is it 5 angle 30?
Have to do the plus minus.
Yeah. Okay, yeah. Yao gave you these tricks all the time, probably in circuits too, right? So 5 sine 2 pi 30t plus 30 degrees. I got to convert this to a cosine. We reference everything to cosine. In other words, that is a cosine, right? There is an equivalent version of cosine that has the exact same thing. How do I get that sine to a cosine? Yeah, basically, I would have to shift it 90 degrees. If it's negative 90, which way do I shift it? Shift it to the left. No, the right. The right, thank you. All right, let's not worry about that too much. So in other words, this guy would be 5 cosine 2 pi 30t plus 30 degrees minus 90 degrees, right?
How to predict it? Plus minus.
If it was plus, it would not be the same. In other words, if this was a plus sign, that would be a non-equal sign.
Gotcha.
So it does matter, yes. Now I could put plus 270 degrees.
Oh, right.
That would be correct, right? This is
Be from pi to negative pi, right? That's when you stay, the bounds when you stay in.
usually, yeah, well, usually we do refer to things in the boundaries between 180 and minus 180. Yeah, degrees. Another point, you said radians, pi and minus pi. I will never use radians. I will always use degrees. I have colleagues that will always use radians, probably. I will always use degrees. The reason I'll always use degrees, if you go to Duke and you say the voltage at this bus is 5 pi over 4 radians, they'll laugh at you. Okay, nobody uses radians, everybody uses degrees. Okay, from a purely mathematical perspective, everything is in radians, right? But I will use degrees. To your question about this, let's not worry too much about the phase shift question. Let's just remember, if I give you a sign, do the negative 90 shift, and that's a trig identity. You can go back to your trig identities. So look at that. But what's that make this phasor here for this guy? 5 over root 2 with an angle of negative 60. Yeah. Okay. All right. So the way I think of it is I look at this picture, right? Is I say that if I have sine, right? The way that I think of it in my head is I say, well, that's what cosine looks like. That's what sine looks like. Hopefully you remember that, right? If I want to turn this guy into that guy, I would have to pull him that direction, right? What is that, the right? I have to pull him to the right by 90 degrees. A shift to the right is always a negative 90 degrees, right? Okay. The other thing I wrote here, phasor analysis only applies in steady state conditions, right? In other words, if I use phasor analysis, I'm not going to get the transient response. The reality is most of the time we don't care, right? If I'm talking about if I'm trying to analyze, let's say a distribution circuit out there in the power grid, I don't usually care about the transient response. Why? Because the power system's been on for a long time, right? Now, you were at my house yesterday, I lost power, right? A lot of you guys probably did too, right? Because of the storms, right? There's a transient then, right? And so in the utility world, sometimes they'll call that cold load pickup, right? Because in other words, the amps, think about it, the amps are actually higher for a little bit during the startup, and you have to be able to deal with that problem potentially, okay? So those are real problems that exist, but they're the kinds of things that happen on the day of a blackout, all right? They don't happen 99.99% of the time, all right? So we don't focus on them as much. All right. Okay. All right. So if I wanted to find, the steady state solution of a circuit like this, right, I'd have to go into phasor analysis. So what would I do to do my phasor analysis here? If I said to you, find me the steady state solution for this guy, what would you do to do that? Yeah, convert the individual pieces here to phasors, right? Right, and what would that end up looking like for me? So I wrote down, let's see, but didn't carry them forward. R is 100 ohms and L is 31.83 milliamperes. Okay. All right, how would I approach this guy? I'd say R is 100 ohms, L is 31, or what did I say, 318.3 millihenries. So how would I figure out the steady state phasor for the current?
R shares on, J's at L goes to gamma L or FL, and then you can do it multiple.
All right, so how would I do that? So I do that, but then what does that mean in terms of what am I solving for? How do I set this up? I think of this in context of there's a total impedance to the whole thing, right? What would the total impedance of this circuit be? Yeah, the impedance of the resistor plus the impedance of the inductor, okay? All right, before we get too down that road, let's just remember real quick impedances, because you said SL, right? We don't usually use S here, right? We're going to use J omega, all right? Now, as you'll find out, again, the power stuff, oftentimes they don't use the L. What they actually use is X. All right, what is X? X is omega times L. All right, we'll talk about that more. But in general, they make the assumption in power stuff, and we're going to see that a lot here, that the frequency is 60. Why do they make the assumption that the frequency is 60? What's the frequency of the voltage right there? 60 hertz. All right. Usually the assumption is that for most things we do, it's going to be 60 hertz. All right. So you're going to see that number probably more often than any other number by far. Okay. All right. So I've got these three basic things. We talked about their relationship, basically their Ohm's law relationship in terms of differential equations. But let's say we want to talk about them in the context of being resistors, capacitors, inductors, and I want to talk about steady state. Okay. All right. If I have a resistor, I guess I already showed it here. What's true about the current and the voltage? Looking at this picture, their amplitudes are different. What's true about their phase? What about those two waveforms out there? What would you say is the phase relationship? Same phase. There's no phase shift with a resistor. Resistor just makes the current bigger or smaller than the voltage. Okay. If I were to say here, what's the phasor diagram? I'd have, how would I draw the phasor for that voltage that I wrote? I didn't give you a formula for it. But based on the voltage V of t that I have right here, what is the angle of that guy? Zero. Right? How do you know it's zero? This is a cosine. Right? I know it's cosine because if t equals to 0, you've got a p. Right? So that's got to be cosine. All right. So these guys, I would say the voltage would be a vector here, and the current would be a vector here. like that. All right, and I do these vectors always with a bar underneath them every time I write it. Yeah. All right, so now for a capacitor. All right, somebody other than this guy over here, what's the relationship between the voltage and the current here? The inductor has an impedance Z. I always do my Z's with the line through the middle of them. What's that? 1 over j omega C. Yeah. Now that's basically two statements, isn't it? Right? That's basically a statement that says that this guy has got a magnitude and an angle. It's probably something you haven't thought about in a while in electronics. What's the magnitude of 1 over j omega C? The magnitude. This is a complex number, right? So what's the real part of said complex number? What's the real part of 1 over j omega C? The real part.
The whole part of the.
The whole thing's imaginary. That's right. So the real part's what? 0. All right. What's the imaginary part? Almost all of it. It would be in terms of being an imaginary part, it has to be A plus JB. Do I have a plus JB here? Well, I don't have an A. I don't have a B quite either. Right? In other words, this guy would really be negative J over omega C, right? So I need J times something. I got the J on the bottom with the 1 over j omega C, right? Yes, this is an imaginary part, but the imaginary part is actually negative 1 over omega C, right? If I wanted to write that in magnitude angle form, let's think about this. Where is that negative J over omega C? Which direction does that point? It would point negative 90. It would point down, right? So this would be Z capacitor here. So I would say that this guy is 1 over omega C with what angle? Negative 90. So it has a magnitude of 1 over omega C, an angle of negative 90. Okay. Now, if I want to relate the voltage and the current there, right? V equals I times Z. It's basically the complex form of Ohm's law. We're going to use this a lot. How many equations is that? What's that? How many? Trick question. Is that one equation? It's 2, right? Because it's complex, right? What are the 2 parts? There's a magnitude and an angle piece here. What would the magnitude and the angle? What's the magnitude equation if I have V equals I times Z? Well, how do I relate? So one vector equals one vector times another vector. How do I relate the magnitudes of those vectors? The magnitude of V equals what? Magnitude of I, yeah, times the magnitude of Z. Okay. What about for the angles?
They add them.
You get a 50-50 shot. Yeah, they add, basically. Yeah. They add algebraically. If I had divided, then there would have been a subtraction, right? So basically the angle of the voltage. So usually I'm going to write my angles like this, like phi sub V. So I've defined everything up there, right? Phi sub V is the angle of that. So phi sub V equals phi sub I plus phi sub Z. Now, that is in general true anytime I got any kind of impedance. But in this particular case, because I have a capacitor, what's the angle of the impedance of that capacitor? What's the angle of the impedance here? Well, we said it's negative 90, right? So phi sub I minus 90 degrees, like that. So I gave an example right here where I had current and a voltage. What do I say? I use a term here. I say that one of the 2 leads and one of them lags. All right. Now, which one leads and which one lags? If I gave you this picture, all right, that's the way I think it is, right? Which one of those 2 waveforms is the leading waveform? Is it this guy or that guy?
It depends on your reference point.
Yeah. Well, it seems that way, sort of, I guess. Way I think of it is, yeah, it does in a way, right? If I look at one individual cycle, right? So I got one cycle in one period. Whichever one comes to his peak first in time, meaning more on the left, more to the left, whichever one comes to a peak first is the one that leads. Whichever one comes to a peak second lag. So if this is I and this is V, who leads? I leads, okay? So, and that's how that manifests here. So it says phi I minus 90 is phi V, meaning that what I have to do is I have to subtract 90 degrees from the angle of the current to get the angle of the voltage, because I is leading. So I have to subtract 90, right? So what's the angle between here and here? I had to basically pull this guy 90 degrees that direction to get to the voltage. That's what this statement says. So in this picture, I would have this. I don't know, I is over here, and V would be over here, more over there than I showed. V would be over here, and the angle between them would be 90 degrees. Now, why did I go that direction backwards? If this is I, why did I do V that direction? Why not 90 degrees the other way? Because it's a negative, right? And if negative is the clockwise direction when we're looking at angles. Okay. All right, now we need to look at inductors too, but I think we're out of time. Right, we go to 210. 215. All right, we're gonna keep going. You guys could have gotten out easy. All right, so inductors, same story, right? What's the impedance for this guy? J omega L. Everybody wants to do LW, right? It's omega. All right, the Greeks don't get credit for a whole lot. They deserve it, right? Z equals J omega L. Now this guy is also complex, right? He has no real part, but he has an imaginary part. I can write him in magnitude angle form as well. What's the magnitude for this guy? Omega L. And what's the angle? 90. Okay. Now, in keeping with that same idea, V equals I times Z. Again, that's two equations, right? So that means that the magnitude of V equals the magnitude of I times the magnitude of Z. What's the magnitude of Z? Omega L. Okay. For the angle, what do I have? The angle of V equals what? Angle of I plus the angle of Z, which is exactly right. Angle of I plus 90 degrees. So the way I think about this is I have to add 90 degrees to the angle of the current to get to the angle of the voltage. That means that the voltage must be leading because I had to add 90 degrees to the current to get to the voltage. So if I draw the picture over here, here's a current. Here's the voltage. Which one peaks earlier in time based on that picture? The voltage, right? So the voltage is the leading one. I have to add 90 degrees to the angle of the current, which means go that direction, go to the left to get to the voltage. All right. I could also say that the current lags the voltage if I wanted to, right? The way that I think about this is the voltage leads the current lags the voltage. I don't memorize anything. All right, there's 5 things that I've chosen to memorize in all circuits. What are they? KVL, KCL, that, Z equals J omega L, 1 over J omega C, and V equals IR. That's it. Those are only 5 things I ever remembered. You might remember there's like Iceman things and all sorts of little mnemonics to try to remember all that stuff. But if you know if you know complex numbers, then you can figure out who leads and who lags always. All right, that's my recommendation. You do you, but that's the way I would recommend doing it, is just remembering those basic relationships. Okay, if I drew the phasor diagram here, what would I write? So in this case, let me ask, let's start with the voltage. Where is the voltage? It would actually be in the first quadrant in terms of the phasor, because you may not, if this guy is peaking before t equals 0, This would be cosine omega t plus something. So I know you gotta have a positive angle. All right. Where would I of t be? This is the voltage. Yeah, he would be over here in the fourth quadrant.
But will you add?
Good question. If this is voltage, right? The voltage is 90 degrees ahead of the current. That's what this is saying. So the current's here. I add 90 degrees, meaning I go in the counterclockwise direction. Mhm. And if I cared about it, I would say the Z, if I wanted to draw that, the Z would be over here somewhere. All right. So your first homework's going to review some of this stuff, all right, as well as get into some single phase power stuff, which we'll talk about on Friday.